Hello everyone, myself Soumya BG, Assistant Professor, Department of ECE SJBIT. In this session, I am discussing about the Module 4 topic of microwave and antennas. In the Module 4, I am discussing about antenna arrays. Antenna arrays. Whenever we tell any antenna, we can represent the pattern of any antenna as produced by an array of point sources. The pattern of any antenna can be regarded as produced by an array of point sources. A point source is a single identifiable localized source of something. I can represent the point source as single identifiable localized source of something. An isotropic radiator is a theoretical point source of electromagnetic or sound waves which radiates the same intensity of radiation in all the directions. This is the isotropic radiator. This is radiating. We can call it as point source or the isotropic radiator. This is a single identified localized source. This can be called as the point source of electromagnetic or sound waves. It is radiating the same intensity of radiation in all the directions, and it has no preferred direction of the radiation. We tell that it radiates uniformly in all the directions over a sphere which is centered on the source. It radiates uniformly in all the directions over a sphere centered on the source. The isotropic radiators are used as reference radiators with which other sources are compared. For example, whenever we want to compare the gain of any antenna, suppose if we want to compare the gain of any antenna, we take isotropic radiators as reference radiators. So basically here we are starting with a point source, and whenever we tell the antenna pattern can be regarded as produced by the array of the point sources. A point source, we can define it as a single identifiable localized source of something, and an isotropic radiator, it is a theoretical point source of electromagnetic or sound waves which radiates the same intensity of radiation in all the directions, and it has no preferred direction of radiation. It radiates uniformly in all the directions over the sphere which is centered on the source. The isotropic radiators, usually they are reference radiators, because whenever we want to do the analysis with respect to other antennas, the parameters of other antennas, we take these isotropic radiators as the reference. As we already know, the antenna is nothing but the component which can radiate an amount of energy individually in a particular direction, resulting in better transmission. And if more elements are added to it, we can expect more efficient output. So in taking into consideration this idea, we have used an invention of antenna arrays was done. This is the antennas arrays. Basically, the antennas, many number of antennas are arranged in the form of the array. The main intention of this is in order to get a better transmission, more efficient output. An antenna array is nothing but a radiating system. This radiating system, it consists of individual radiators and elements. The antenna array is basically a radiating system. This consists of individual radiators and the elements, and each of these radiator while functioning as its own induction field. Each of this radiator, when it functions as its own induction field, and here the elements will be placed so closely that each one lies in the neighboring's own induction field. The elements, that is the antenna arrays, are being placed such that each one has to lie in the neighboring one's induction field. Hence we tell that the radiation pattern produced by them will be the vector sum of the individual ones. As we are already aware, the antenna can radiate an amount of energy in a particular direction. It is being used individually and results in better transmission. So instead of using a single antenna, if we use many number of antennas in the form of a array, we can expect more efficient output. So an antenna array, we can define it as a radiating system which consists of individual radiators and elements, and each of these radiator will functioning as its own induction field as well, and these elements will be placed so closely that each one will lie in the neighboring one's induction field. Therefore, we tell that the radiation pattern produced by them will be the vector sum of the individual ones. This slide gives the examples of some antenna arrays. This is a linear array example. These are the dish antennas which are arranged in the form of a array. This is a planar array. This is a two-dimensional array of microstrip patch antennas. Now let us concentrate on the advantages and disadvantages of these antenna arrays. The spacing between the elements and the length of the elements according to the wavelengths should also be kept in mind while designing these antennas. And these antennas, they radiate individually, and while in array, the radiation of all the elements, they will sum up in order to form the radiation beam, and this will be having high gain, high directivity, better performance, and the loss will be minimum. So based on this, we can just list out the advantages and disadvantages. The advantages of using antenna arrays will be, the first is basically from this the signal strength increases, high directivity is obtained, the minor lobes will be reduced, the signal to noise ratio achieved will be high, the high gain will also be obtained, the power wastage is reduced, the better performance is obtained. Coming to the disadvantages here, the resistive losses are more when we use the antenna array. The mounting and maintenance will be difficult, and huge external spaces are required for these antenna arrays. Let us just repeat the advantages and disadvantages here. The advantages are the signal strength increases, the high directivity is obtained, the minor lobes will be reduced, high signal to noise ratio, high gain, the power wastage is reduced, better performance is obtained. And coming to the disadvantages, the resistive losses are increased, mounting and maintenance is difficult, and external space required is also huge. Let us now know the applications and types of arrays here. Coming to the applications, the antenna arrays will be used in satellite communications, they are used in wireless communications, they are used in military radio communications, they are used in astronomical study. And coming to the types of arrays, the basic types of arrays are collinear array, the broadside array, end-fire array, parasitic array, Yagi-Uda array, log periodic array, turnstile array, and super turnstile array. In this, we need to discuss about the broadside array and end-fire array. Now let us understand the output voltage that we get when we consider the antenna arrays. To do the analysis in a simpler way, let us consider only two antennas, or we call them 2 point sources, and these 2 point sources, they need not be having same amplitude as well as phase. So based on that, we can actually make 4 type of cases in which the two isotropic point sources may be having same amplitude and same phase, same amplitude and different phase, same amplitude, equal different amplitude and same phase, and different amplitude and different phase, like that. We can list out the 4 cases here, and let us have an understanding with respect to the case 1. In the case 1, let us consider the point sources. These 2 point sources are isotropic, it means they are radiating energy in all the directions here. Let these point sources be 1 and 2, and they may be separated by the distance d, and they are located symmetrically with respect to the origin of the coordinates. As we can see here, there are 2 point sources 1 and 2. They are separated by the distance d, and they are located symmetrical with respect to the origin of the coordinates. So distance from the origin for point source 2 is d by 2, distance for the point source 1 is d by 2. And when we consider any distant, when we want to find out what is the reception available, how the signal is being transmitted at the distant point, which is at a distance r from the origin, corresponding to the x direction, if the angle pi is being considered, the angle pi is measured counterclockwise from the positive x-axis, and the distance between these two point sources is 1 by 2 lambda, that is of wavelength distance, and the origin of the coordinates usually is taken as a reference for the phase. And this is a case in which we have both the point sources are having same amplitude and phase, and since they are having same amplitude and phase, when we consider the distant point from each point source, from point 1 and point 2, as you can see here, point 2 is nearer to the distant point compared to the point 1. So when I tell point source 1, it is actually having a retardation with respect to the point 2. So the total field potential with respect to distant point from the source 1 is represented as E naught exponential of minus j psi by 2. From source 2 it is represented as E naught exponential of plus j psi by 2, since it is nearer to the distant point compared to 1. These two now sum up and they results in the total electric field E. Now at a distant point in the direction pi, the field from source 1, as I told just now, is retarded by of dr cos pi, while the field from source 2 is advanced by of dr cos pi. Here dr is the distance between the sources, which is expressed in radians, and dr can be represented as 2 pi by lambda into d, where 2 pi by lambda is nothing but beta, so beta d. Let us take this as expression 1. At a distant point in the direction pi, the field from source 1 is retarded by half dr cos pi, while the field from source 2 is advanced by half dr cos pi. Here dr is the distance between the sources expressed in radians. Dr is equal to 2 pi by lambda into d, that is equal to beta d. And a total field at a large distance r in the direction pi is then, the total field at a large distance r in the direction pi is then given by E is equal to E naught exponential of minus j psi by 2 plus E naught exponential of plus j psi by 2, where this psi is nothing but dr cos pi, and the amplitude of field components at the distance r is given by E naught. So this equation 2 may be rewritten as E is equal to, we can divide as well as multiply by 2, so 2 E naught into E naught becomes a common here, exponential of plus j psi by 2 plus exponential of minus j psi by 2 divided by 2. We need to express this in terms of mathematical equation, that is why we are doing this rearrangement. So finally the electric field E is equal to 2 E naught into, because exponential of plus j psi by 2 exponential of minus j psi by 2 is nothing but cos of psi by 2. So this is again equivalent to 2 E naught into cos of, and the value of psi is what, dr cos pi. Let us substitute that. So dr cos pi by 2, and we know that psi is equal to dr cos pi, and already we know that dr, that is the radial distance, is nothing but 2 pi by lambda into d, and again d is equal to what, of wavelength, that is lambda by 2. So dr can be written as 2 pi into lambda by 2 divided by lambda, that is equal to pi. And we can still normalize this equation 3. In order to do the normalization, we just said 2 E naught as equal to 1. Finally, the expression for the electric field for the first case, in which there are two isotropic point sources of same amplitude and phase, can be given as cos of pi by 2 cos pi, cos of pi by 2 cos pi, because the value of dr is what, pi by 2 cos pi. This is expression number 4. Let us now derive the field pattern for this first case. For this first we need to find out the maximum field direction, that is pi m. The maximum field, it means the peak value, it is in pi m direction, and it is actually obtained by considering the equation 4 angle as equivalent to plus or minus k pi. means we take the angle of equation 4, that is pi by 2 cos pi, and we are considering the maximum field, that is pi m. It has to be equalized to plus or minus k pi. Here k value ranges from 0, 1, 2, 3, etc. And when I substitute the value of k as 0, we get the maximum value of the angle as pi m as plus or minus 90 degree, and there is a major lobe maximum angle, and for k is equal to 1, we get pi m as infinity. Similarly, for phi is equal to 2, k is equal to 3, etc., the pi m value becomes infinity. So, the value that we get for the maximum peak in the pi m direction for the major lobe particularly is pi m is equal to plus or minus 90 degree. Now, let us move on to the null field direction. The null field direction means there is no field, there is no signal in the field pattern, that is pi naught. We can represent it as pi naught. This is obtained by equalizing the equation for angle to plus or minus 2k plus 1 into pi by 2. That is, we are equalizing pi by 2 cos pi naught is equal to plus or minus 2k plus 1 into pi by 2. Again, for this also has got k value ranges from 0, 1, 2, 3, etc. For k is equal to 0, we get 4 hangers here, because LHS also plus or minus and the RHS is also plus or minus. So, we get pi naught as plus or minus 0 degree, and one more angle is plus or minus 180 degree. For k is equal to 1, and the remaining cases the pi naught value is infinity. Next, coming to the off power field direction pi hp, it is obtained by equating equation for angle to plus or minus 2k plus 1 into pi by 4. It is, we are equating pi by 2 cos pi hp to plus or minus 2k plus 1 into pi by 4. In this case, if we take k as 0, pi hp will be equal to plus or minus 60 degree as well as plus or minus 120 degree. As I told, there is plus or minus on both left hand side, LHS as well as RHS, so we get 4 hangers. And for k is equal to 1 and k is equal to remaining cases, pi hp is infinity. So, let us brief out the angles now. For peak, the pi m angle is plus or minus 90 degree. For null, it is plus or minus 0, plus or minus 180. For off power, it is plus or minus 60 degree, plus or minus 120 degree. This is how the radiation pattern will be here. As we have found out, the peak actually occurs is 90 degree, and this is a null angle 0 degree and 180 degree, plus or minus 0 degree, plus or minus 180 degree. And this is the off power beamwidth value, the plus or minus 60 degree, plus or minus 120 degree. The field pattern of E versus pi as expressed by equation is being shown in this figure C. And this pattern is a bidirectional figure of 8 with maxima along the y axis. This pattern is a bidirectional figure of 8 with maxima along the y axis. The space pattern is definite shaped. As you can see here, the space pattern is definite shaped, and being a figure of revolution of this pattern around the x axis. So, this is how the radiation pattern will be for the first case. So, in this session we discussed about what is antenna array, what are the advantages of antenna arrays, why we need to use antenna arrays, what are the disadvantages, and how do we analyze the total voltage that we get by means of antenna arrays by considering the cases. The first case has been discussed, that is, we have discussed about 2 isotropic point sources of same amplitude and phase. Thank you.